Okay, fine. So let's get started. In the last few classes, we had been dealing with statistical models for spatiotemporal processes. We have talked about the geostatistical equation. We have talked about like Gaussian process and so on. And we saw that how we can actually fit some kind of a probabilistic model on the spatiotemporal process that we are observing, and how with the help of that probabilistic model we can make predictions, or like we can estimate the values of the variable at location at spatial or temporal points where we do not have the observations. So like that is, we saw that like with the help of Gaussian process regression, that is, if we have observation at a few locations, we can actually estimate a spatiotemporal function over that the spatial function over the entire region, and from that function we can find out like we can predict with along with probability distributions possible values at defined other points. Now today we will look at a slightly different topic. So suppose even if we do not go for probabilistic modeling and things like that, even otherwise using simple ideas from data mining, like say things like clustering and nearest neighbor prediction, decision trees, these kinds of things, it is possible to answer some questions. So that is known as spatiotemporal data mining. So the one of the basic problems, or the one of the most common problems which we come across in this domain, is the problem of missing values. That is, you have a spatiotemporal data set where there are a large number of values are missing. Like it's may have happened due to the sudden failure of a particular sensor, or these kinds of things. So of course, if you build the kind of probabilistic model or the Gaussian process model which we have been discussing, then of course it is possible to estimate the values of these missing I mean it's possible to estimate these missing values, but as you would have understood, it requires quite a bit of modeling. It requires to fit a model with lots of parameters, do like lot of computations and so on. But in certain situations, it might be possible to, like where the data set is maybe slightly smaller and the processes involved are maybe less complex, it may be possible to do something much simpler based on intuitive ideas. That is something which we will try to understand in today's lecture. So before going into this, let us first consider a few terms which are going to be useful here. I mean, in the domain of earth sciences. So one is anomaly. So anomaly, like as you most of you understand by anomaly, is something like some a different behavior than the usual. Those of you who have done machine learning projects would have heard of anomaly detection, right? So can anyone mention any application of anomaly detection which you may have come across in any project? Yes, anomaly detection. Anyone is familiar with the idea? Yes. So And so anomaly detection is basically, suppose you have like a large volume of data or observations in which there are certain points which are which are different from the other points. So identifying those different points like that, roughly, that is called the anomaly detection in normal applications. Say for example, say suppose there is a gas sensor which has been recording the concentrations of a certain kind of gas, and the gas concentration usually remains at a particular value, but there are like maybe for some time it had suddenly increased. Now that can happen either due to a gas leak or due to some kind of fault in the sensor itself, due to which it was, or maybe some electrical fluctuation or something, power interruption or something like that. It was giving whatever it is, it's a matter worth investigating. So in such situations, to identify these kinds of unexpected or deviant behaviors in the data, people you go for anomaly detection techniques. Now, in the domain of earth sciences, anomaly has a slightly different meaning. Anomaly is like basically the deviation of a particular observation from the usual value of that observation. So consider this example. So suppose we are measuring the daily temperature in Kharagpur. So like let us say X is the temperature and S at a given any location S and at a given time T. Now, if you consider only the location, we can define mu of S as the local mean or the climatology at that location S. That means if you take the average temperature at that location over a long period of time, what you will get is basically mu S. Similarly, we can have mu T also. Right? That is, if you take the average over time, instead of at a given time, if you take the average over all the of a large number of locations, then what you will get is the temporal mean, right? So and then similarly, you can get define spatiotemporal mean also. So so these examples will help you to understand what these things may mean. And now, suppose you have fixed the location and a time period. Let us say the temperature in February in Kharagpur. Okay, so this has it has a long-term value. That is, suppose you have observed many February months in Kharagpur, and you have like over say 100 years, and you have calculated the mean temperature. So that is the climatology. Now, when it comes to this particular February, say the February of 2022, if you calculate the mean temperature over Kharagpur, so this is going to be some so you will get the value of this observation. Now, obviously, that observation is not going to exactly match the mean temperature over the past 100 years. It will be either slightly hotter or slightly colder, maybe much hotter or maybe much colder, whatever it is. This difference is called the anomaly. Okay. So now this kind of anomaly, obviously it can be positive, negative or zero. Zero it usually isn't, because it's the temperature in this case at least is a continuous variable, and it is like very unlikely that it will be exactly equal to the 100-year average or something like that. Now now these kinds of anomalies, these are often spatially or temporally coherent, right? So it means that, like, suppose at any given time the temperature in Kharagpur, the mean temperature in Kharagpur is higher than usual. That is, it has a positive anomaly. Then it's very likely that the surrounding regions are also going to have a positive anomaly of the temperature. Now, the amounts or the magnitudes of this anomaly may be different in the different locations, but like the signs usually tend to agree. Okay? Now, when several regions, or I mean several locations in a given region, if they simultaneously have a anomaly of a large magnitude, that is called an anomaly event. So suppose there is a heat wave kind of thing where I mean a heat wave is usually not a very localized phenomenon. It affects like a significant geographical region. If such a thing happens, then like we can say that several places or several locations or several values of S, so to say, are simultaneously experiencing a positive anomaly of a high magnitude or a negative anomaly of high magnitude. So such situations are known as anomaly event. And so clearly an anomaly event can be either positive or negative. Like for example, heat wave is a positive anomaly event with respect to temperature. That is when several regions have a significant rise of temperature that lasts for a few days. And on the contrary, drought is a negative kind of anomaly. It happens. It's a negative anomaly event with respect to rainfall. That is when there is less rainfall or very less rainfall compared to average in a given region, and lasting typically for several months, maybe even a year. That is called like that. That's an example of a negative anomaly event. And now let us consider any random data matrix like this. So you can say that there are 6 spatial locations and there are say 5 temporal locations, and this the value is any geophysical variable which is of like it may be like we are not specifying what it is, but you can say that it has got these values. Okay, now by looking at this matrix, uh, like there are certain observations which you may want to make. So can you tell me some observations you are able to make from this kind of a matrix? Yes, anyone wants to hazard a guess? Like, do you see any kind like all these values? The values by themselves don't mean anything significant, but is there some kind of pattern which you may be observing?
The values are between like 14 and 30, 35, 38 something.
Okay, fine. That's definitely correct. Anything further? Okay. Let us let's forget that. Now let us look at this matrix. Suppose there are some values are missing, and the task that has been given to you is to predict these missing values. Okay, so if you have no now suppose you forget that this is spatiotemporal data. Suppose there is a matrix, just a matrix like this containing some arbitrary numbers and some values are missing from that matrix, and you are asked to predict the missing values. So what will you do? Obviously there is nothing much there, you have nothing much to say about it. I mean, it's a random matrix in which some values are there. You do not know any kind of structure in the matrix, and like some values are missing at random. So there is probably no way in which you can predict the values. Now uh, so in general that is true, but in some situations you may be able to do that also if you can see some kind of structure in the matrix. So in the if you look at the current matrix, so this matrix is like, although it may look similar, but there are subtle differences between this matrix and this matrix. So by looking at this matrix, can anyone identify some kind of structure which may help in predicting the values of these missing variables?
In each time, mostly that like the measurements are decreasing. Like in T1 from 32 to 15, from T to 30 to 14, like
Okay.
that.
Okay, fine. That's a good observation.
Sir,
So,
there are repetitive observations like 32, 32.
okay. Uh, like, how about, so there are 6 spatial locations. So, can you make any, or can you observe anything related to these 6 observations? These 6 locations. Can you say anything about these 6 locations? Does anything strike?
Like S1 is like at higher measurement and decreasing to S6.
Okay, fine, right? Whatever is that you already said, from S1 to S6, there seems to be a decreasing tendency. But still, can you make it a bit more specific than that? Anyone else? So you may observe, like, can you see that? Do you think that S1 and S2 values are usually similar to each other compared to say S2 and S3? You can see that the difference between the values of S1 and S2 is usually quite small, like a 1, 2, etc. But if you consider S2 and S3 or S1 and S3, the differences are larger. Here is 8, here is 9, 7. But if you consider S3 and S4, again the differences are small. Here it's 2, here again 2, etc.
So the data has covariance stationarity.
So what is the what is the rough structure of that covariance? What is the rough covariance structure? Okay. Okay, so like if you observe these kinds of differences on like again on the basis of these differences, can you say something now about these 6 locations? Quick. I think this should be pretty straightforward now. It seems that S1 and S2, these two locations are close to each other or somehow strongly related with each other. Similarly, it seems S3 and S4, it's like another set of locations which are like where that variable is usually related. Similarly with S5 and S6 also. So we can roughly say that there are 3 clusters of locations. S1, S2 is one cluster, S3, S4 is another cluster, S5, S6 is a third cluster. You can see that between S1 and S2 in both for cases of both S1 and S2, the mean reading seems to be around 30, 31 or something like that. In case of S2 also, the mean reading seems to be around 32. If you see S3 and S4, their mean readings are roughly around 26. In case of S5 and S6, it's much lower, right? So we can roughly say that we can roughly identify some kind of clusters of locations. So maybe these 2 locations are from one region, these 2 locations are from another region, these 2 are from a third region, etc. etc. If you see temporally, if you go along the 5 time points, then can we see some kind of a trend? From T1 to T2, we see here we see a small decrease. Here again we see a small decrease. Here also we see a small decrease. And from T2 to T3, here we see a small increase. Here we see again a small increase. Here we see a small decrease. T3 to T4, here we see a small increase. Here we see a somewhat bigger increase. Here we again see a small increase. T4 to T5, slight decrease, equal, slightly larger decrease, etc. etc. So based on this, any comment, like can you make any comment about the temporal variability, the variation with time?
There is some periodic like change in that variable across time.
Right, so it's like once decreasing, again increasing, again maybe again slightly again increasing, again decreasing. So we can say some amount of periodicity, you may say. Apart from that, anything else? Are the changes that take place like like from one like when from one time point to another, when a change take place, does it uniformly impact all the locations, or like is the change different in different locations? Yes, what is your observation? We see that the change whenever the like one region is impacted in some way, the other regions also seem to be impacted in a similar way. Here it goes down, here it goes down, here also it goes down. So all the changes seem to be happening are synchronized with each other. Okay, but the catch is of course that the magnitudes of the changes are not much, from 32 to 30, 25 to 23, 15 to 14. It's like nearby only, but if there is a slight decrease, then it seems to be affecting all the places. Similarly, here there is an increase. Like here there is an increase, here also there is an increase, here there is a decrease. So it's like, okay, this one we can say it may be considered as like aberration. So in case when we are dealing with real spatiotemporal data of geophysical systems, we will never see any perfect relation. There will always be imperfections or exceptions. Here again we can see that like it seems the value seems to have increased in all the places, and again here it seems it has either decreased or remained the same in all the places. So it does seem that whenever there is a like on any given day, if there is an increase, then all the locations are like we can make a kind of a guess that on any given time point, if there is an increase, like most of the locations are going to experience an increase. If there is a decrease, most of the locations are going to experience a decrease. So now let us try to do some kind of interpolation. Okay, so so interpolation is of course something you all of you roughly know how to do. So suppose like you are given this kind of a matrix where like some values are missing like this, and you are now required to predict the missing values. So like earlier, so this is a problem which we had earlier talked about, predict the missing values. At that time we saw that if nothing is known about the structure of the matrix, then there is not much we can say anything about it. But now there are certain structures which we have been able to which we have identified from the matrix, right? So in the light of those changes, can you come up with some simple heuristics of predicting these missing values? Quick, please respond. Anyone wants to volunteer? If you are asked to predict these missing values, what would you do? Anyone wants to answer? Samarpita? If you have to predict these missing values, what would you do?
We'll use the spatial clustering relation and the periodicity observed in the temporal.
Okay, fine. So can you explain with the help of an example? So suppose you are asked to predict this value. What exactly will you do?
We'll consider that that S1 and S2 are closely related spatially, and the periodic relation, like from T1 to T2, how it is decreasing from T2. We know how T3 and T4 is varying for S2, and we know that S2 and S1 are spatially related. So we'll use that relationship.
Okay, fine, thank you. Okay, fine, that's a good answer. So now let us first things first let us consider the simplest thing. So even before we consider the as Samarpita said, of course we need to consider the effects of the other locations as well as the temporal variability. So for if we want to predict for S1, we have already seen that S1 and S2 seem to be like in some kind of a cluster. So here in this case I do not have the value at T4, I do not have the value at S1, but I do have the value of S2, and I know that the value of S1 is usually close to that of S2. So I would like we can say that 30 like the 35 is something like we can say is a base case estimate. Now apart from that, there is a temporal variability also. So we see that from T3 to T4 at S2 there has been an increase of 1. So that is seen in that way that like if the same increase happens here also, in that case what we should be getting here is 33. But on the contrary, from here from T4 to T5, S2 has experienced a decrease of 2. Here, if T4 is to be 33, then this decrement will be 1, which is like so it's like there are pulls in 3 different directions. One is the pull towards this value, the other is a pull towards this value, the third is the pull towards this value, right? So basically we have to so there are like multiple constraints which we may want which we may want to like consider. So but before doing anything else, what we can do is, even before taking the spatial or temporal correlations etc. into account, the first thing which we can do is just to calculate the local means. Okay, so that's probably like when I first asked this question, I thought some of you would try to say this, that first of forget the spatial or temporal relationships. What about the local mean? The local, at every location you can just calculate the spatial mean. At S1 you have one missing observation, but you have four observations, so you can take its mean. So similarly at all the locations you can calculate their means. Okay, and the simplest thing which you can do is, whenever you don't have the missing like when you have a missing value, you just put the mean value of that location, right? That's probably the simplest thing you can think of. Another possibility is the temporal mean. Instead of taking the spatial mean, you just like for every single day you take the temporal mean. Okay, and then so if on this day this temporal mean comes to 26.4, here one possibility is to put 26.4 here. Okay, and so on. So in this case, between the spatial mean and the temporal mean, which is the one that you will prefer? So so obviously in this case you will be preferring the spatial mean. Why? Because like if you consider, because there is significant amount of spatial variability here, but the temporal variability is much less. That is, when you are taking the mean over time, you are basically that is taking a mean makes sense only when there is less variance along that dimension. So if we take location over space, there is a lot of variance over space. So like we have already seen that S1, S2 is one cluster, S3, S4 is another cluster, S5, S6 is a third cluster, etc. So taking so if we are to take the mean over the locations, then we are basically ignoring all those differences. So like just by looking at it, you can understand that putting 26.4 here is probably not a very good idea, because we know that S5 and S6 are usually close to each other, and that and their values are like quite low. So 26.4 does not seem to be a possible value here for S5. Right, so if we have to take this kind of a mean and replace the missing values, then you have to take the mean only over such values where there is reasonable amount of uniformity, right? So taking the at a particular location, taking the mean over time in this case seems to be a decent idea, even though there is temporal variability, as we have already pointed out, but that is like relatively minimal, so we can still take them. On the other hand, this one does not make any sense. The other possibility, so but this is like a very first order thing which we can do. If we do not know anything else, then we can do it. So here when we are doing that, we are basically treating every location and every time point as independent of each other. But we can clearly we can do better, because we have already identified that there are some spatial structures as well as some temporal structures. So as just discussed, we may want to incorporate all those structures while making the prediction. Okay. So now when there is like some kind of an anomaly, now so like let us say the XST, this is the observation at any location S and time t. So this can be decomposed in the following way. One is the mu s. This is like the climatology at the local mean at the given location S. plus eta st plus est. Now, what is eta st? So if you so this is like related to the geostatistical equation which you had studied last week. So eta st is like the global effect and est is the random effect. EST is like basically like the, we can say that it is specific to that that location and that time, and it is treated as a some kind of a random noise, right? That is how we define the geostatistical equation. That is E of ST is basically, it follows a Gaussian distribution which is like independent for at all the locations as well as look in at the time points. So this is, it's like EST, this is an entirely an unpredictable thing. Why do I say unpredictable? Because the way it like EST, because it is done independent of every other location, it is at and every other time point. So so it is not related to anything else, right? So if it is not related to either other locations or other time points, we cannot like use the readings at other locations and other times to make any guess about it. So this is called the unpredictable part of the anomaly. This is like so whatever, and this is like the predictable part. This is some like the global component, which is basically the influence of the other like other locations and maybe the other time points also. So this part we can never, we may never be able to predict. Our predictions will be limited to the this part. So the base value or the climatology will always be there. On top of that, we have to like if we have to make an estimate of xst, suppose xst the this value is missing, I do not know it. So then we, this mu s is the climatology or the long-term mean at that location. EST is the unpredictable part, and eta st is what is that part which you can estimate from other locations and other time points. Okay, so so now let's come back to the same problem. So the estimated climatology at all the locations is basically the long-term mean, the mu, so as to say the mu of S1 is this thing. So you can, like as you can see in this case, what we have probably done is just taken an average over these all the values that are available. Actually that need not be the case. We should actually take the climatology over a long, say 100 100 years or something like that. But of course, if that is not available, if only this much is available, then this is all that we have to do with. Okay, so the first part, the mu s, this you can say is coming from here. Now, okay, so I should also mention here is here I have written as mu s, but it need not all be mu s in all situations. In some situations, it may be more pertinent to use mu t, that is the average over all locations for this specific time point. But in this case, as we have already seen, that does not seem to be making much of a sense. That is, we cannot take the average over space because there is a lot of spatial variability, but we can take the average over time because there is very less temporal variability. That's why we are like looking upon it as primarily as a spatial process. So we are using mu s. But if it had been the other way, like if the variability had been more along the temporal axis and less along the spatial axis, then we may have considered it as a temporal process also, in which case we would go for mu t. Or it might have been a spatio-temporal case, that is, their variability may have been both along the spatial domain as well as along the temporal domain. So in which case we would have like gone for some mu st, this kind of thing. But here in this example, let us limit ourselves to mu s, just for understanding. And now let's try to do the anomaly prediction. So you have to, so now here talking about the eta part of the anomaly. Right, so so eta of ST is basically the mean of the neighboring anomalies. What by neighboring, what I mean is spatially neighboring as well as temporally neighboring. So it's basically some kind of a simple autoregression. So what did we do when we studied autoregression? What did we do? We were trying to estimate the value at one location or one time point in terms of others, right? So like for example, like x t1, we were trying to write it as a times ax t2 plus b of x t3, etc, etc. This is one way you can look upon it, or you can also like maybe this you are doing for like for a particular location, or if you want you can do it somewhat like this also. S1t, you may do it as say a of x s2t plus b of x s3t. This way also you may want to do it. So like this is of course the temporal autoregression, and this is the spatial autoregression we have already discussed. So what we are talking about here is basically some simplified version of this. Simplified I'm saying because it's like you need not actually have to estimate all these coefficients a and b. I mean, it's great if you actually do that, but like sometimes even taking a simple mean can also do. But the interesting thing here is that only certain I mean, here you are not going to use all the locations as the predictors, or like you are not going to use all the time points as the predictors. Only the neighboring locations can be used as predictors. Now, what do I mean by neighboring? So we have not been given coordinates of these locations in this case. So we do not really know what is meant by neighboring. But yeah, so in a typical problem, you may have the coordinates of I mean the latitude, longitude, or some other kind of geophysical coordinates of the locations. So, or not do we know the the actual values of these time points, that is, or the timestamps related to them, how much is the gap, etc. That we do not know. But still we have already like by looking at the values, we have identified that s1 and s2 are like they are they are always having similar values, so probably they are neighbors. Similarly, s3 and s4 are probably neighbors. S5 and s6 are probably neighbors. So when I will try to estimate this missing value, I will take the help of only s2, because s2 is the only neighbor of s1, not any of the remaining things. Okay. On the temporal side, like we have seen that there is not so much of temporal changes, so we can take both t3 and t5 as the neighbors. So now suppose what we can do is, first of all, let us reduce the data set to that of the anomalies. That is, for all the observations, let us just reduce to anomalies. So what is anomaly? Like anomaly, as we have already discussed initially in the first slide itself, is the difference between the observed value and the climatology. What's climatology? The long-term mean. So here if you see this table, this value, this is the value of the observation 32, and the estimated climatology is 31.5. So obviously the anomaly here is going to be 32 minus 31.5 equal to 0.5. So we put 0.5 here. Similarly, at all the other locations and all the other time points, we just subtract this climatology and we get the values of the anomalies. Okay. So now we have basically we are dealing with the anomaly data. So again, just to remind you that x at any given location, x st is equal to mu s plus eta st plus epsilon st, the error. This is something which we will not be able to predict, so just forget it. Mu s, so like what we can write this as eta st is equal to x st minus mu s. Okay, so like let us calculate. So like this is basically the anomaly. So let us calculate the value of the anomaly wherever it is possible. Wherever there is, wherever it's possible, as in like we do not have the observation of x at all the places. Wherever we have, we just calculate it. So that so basically this way, what we got is the value of the eta. Okay, and the eta which we have seen that this is the global component. That means this like what this has a property of spatial and temporal correlations. So if you like, so if there is like there is some kind of change between these two locations, it will have to, like I mean like it is expected that there is we will find some kind of special correlations between the this part I mean the anomaly in S1 and that in S2 and so on. Okay, so so first of all, let us consider the three clusters separately. So like S1 and S2 we are already considering as one cluster, S3 S4 we are considering as one cluster, S5 S6 as another cluster. So let's just with the help of this kind of color coding, let's just set them aside as or set them apart from each other. Now if you want to do the interpretation I mean interpolation of the anomaly from only the taking into account only the spatial factor, so here not the temporal factor, so here you may see that here on this at T4 there is the anomaly in S2 is 1.25, so you may just put 1.25 the same value here also in S1 also. Similarly, all the other locations you can just wherever there is a missing value you can just put the like the neighboring locations anomaly value we can just put in here. I'm not saying that is the again that's like the best thing you can do, but it is one of the things you can do. So the you can say the first level approach would have been just to consider the spatial location, the spatial climatology, and wherever that value is missing, you just assume that the anomaly is 0 and you put the that climate the long-term mean value there itself. That is the first order thing which you can do. The second order thing which you can do is something like this. You identify, like you divide the data set into spatial neighbors or temporal neighbors as necessary, and like you just copy the value of the spatial means or the temporal I mean the mean values of the spatial neighbors or temporal neighbors as the case may be. So in this case, of course, there is only one neighbor, or each one like S1 has only one neighbor, namely S2. So taking the mean basically means using the same value itself. Had it if it had more neighbors, then we would have taken the mean of the anomaly values of those and put it here. Okay. Now, but again, this is only one kind of thing. So so that way we would like maybe these are the kinds of values we which you'd get, and so on. But maybe you can do something better than this. Maybe you can take the temporal anomalies also. So that is like instead of considering only that is instead of just copying the value of S2 at T4, you can maybe you can do something like you can also like whatever value is. So it's like what you can do is somewhat like this. So just a second. Yeah, so in let us say this x. So so here so like here so here what you can see is the like if you consider the spatial difference between here and there, it's like x minus 1.25. Let's put the take the absolute value of this. Then let us take the temporal difference between this and this. So that is like it's like x minus 0.5. and this is, and here also it's the same difference, x minus 0.5. So now, but what can you expect these values to be? So here you can see that x minus 1.25, it's like basically how much do you expect the difference between these two readings to be on the same day, right? So what you can do is, you can, in all those days where both readings are available, you can see what their difference usually is. So on day T1, this difference seems to be like quite large. It seems to be 1.25. Okay, here the difference is much smaller, it's just 0.25. In this case, again, the difference is quite large, 1.25. Okay, so you can see that like if you take the average of these three, so 2.5, you will get 2.75. So let us say something like 0.9, let us say. Okay, so we can say that this difference is usually about 0.9. Okay, now if you consider the difference between T4 and T5, so in general, what is the difference of the readings between T4 and T5? So here if you see that the difference seems to be, here it is 1, here it's 4, and here again it seems to be 2, right? So 1, 4, 2, their average is 7/3, means like let us say about 2.5. So this difference we expect to be about 2.5. Okay, and similarly, if you consider the difference between T4 and T5, so like here the difference is again 2. Here the difference is 0. Here it is 4. So 2, 0 and 4, their mean value is 2. So again you expect it to be 2. Okay, so basically you like whatever value you are estimating x, it's like it should satisfy these constraints as much as possible. Now there may not be a single value x which can satisfy all these equations simultaneously, so you have to go for something like a least square minimization or something like that, and by solving that you can try to get the estimate of x. Okay, so that is like you can say that is the optimal way of solving this problem. Now this so it's like it's a very localized method. It's like for every single anomaly you are picking up one by one and solving it locally, purely on the basis of the spatial and the temporal neighbors of that value. Okay. Now there are some other approaches also which allows you to do this using some matrix based operations. Now it will not always work, but but if the matrix, if the full data matrix, if the full spatiotemporal data matrix that we started with, if it is like a low rank matrix, then there are ways to solve the problem. So like if you consider, like let me give you a very simple example. Okay, so suppose I have given you this matrix and I have asked you to predict this value, these two missing values. So probably, of course, there is nothing like, there is no way in which you can make the prediction. Now suppose I reveal one of these two values to you. Suppose I tell you that this value is 2. Okay, now you have to predict this value. Still there is no way in which you can predict it. Why? Because there is no constant which I have defined on the matrix. It can be anything in the world. There is no reason why I should guess this or the other. But suppose now if I tell you that this is such a matrix whose rank is as low as possible. Okay, I have not specified how low, but I'm saying it is as low as possible. In that case, can you tell me what is this missing value?
2.
And why so?
Because least rank possible is 1, and the second row should be like the linear combination of the
right. Correct. So if you know that the rank should be as low as possible, as you correctly said, in that case, so I like either in this case, because it's a 2 cross 2 matrix, there are only two possibilities, either rank 1 or rank 2. So if I say as low as possible, that only means rank 1, and rank 1 means this row is a linear combination of this. So if that is the case, here you can see the scaling factor is 2. So here also the scaling factor must be 2. So the answer is 2. Correct. Now, if I, instead of a 2 cross 2 matrix, if I take a, let's say 4 cross 4 matrix, or a 5 cross 5 matrix, something like that. Okay, and then some values are missing at random. Okay. We did, I mean, it does not even have to be a square matrix. So let us say that as this value, this value, this value, and this value are missing. Okay, so can you fill them up? In general, no. But if I tell you that like its rank is low, then there is a chance that you may just be able to actually guess it. So there are two possibilities. One is that you exactly guess it. The other is you can give some worst case guarantees, meaning that the guess which you have made may not be the perfect guess, but the net error which you have made cannot be more than a particular value. Okay, so that is, let's say that the values which you have predicted here are, or let us say the actual values here are A, B, C, and D, and the values which you have estimated some by any way are A hat, B hat, C hat, D hat. Then it's theoretically possible that you will be able to say that A minus A hat square plus B minus B hat square plus C minus C hat square plus D minus D hat square will be less than equal to some particular threshold value which. So so there are algorithms which try to solve these things exactly. Now whether they will be able to solve them exactly or not is a different question, but at least they can give a value, like if they can give some kind of a guarantee that even if I do not give you the exact values, the values which I will give you, they will not be too bad either. So that is one way of solving the problem. Like if you consider the case which we have been considering, anyway, that itself may be like this kind of a guarantee may actually be enough, because we were anyway having to solve these kinds of equations, right? In which case we would anyway have not got the perfect value. And plus you remember that epsilon st factor was there, the random noise, that is anyway an unpredictable part of the value. So that is guessing the exact value is anyway not something anyway not something which we can do because of the presence of the that thing, the random component, right? So so if you are considering the real world geophysical data in which you are trying to do this kind of a problem, there is obviously no hope of an exact guess. But if you can do this, give this kind of a guarantee, that's good enough. Okay, now of course this will be possible only under the assumption that the data is low rank, or at least approximately low rank. What do I mean by approximately low rank? Approximately low rank, so what is a low rank matrix? We all know that is the different rows or the different columns are like not linearly independent. In other words, each row can be expressed as a linear combination of the other rows. Similarly, each column also. What do I mean by approximately low rank? It means that the matrix itself, the given matrix its rank is not low. It may be a full rank matrix, but there does exist a low rank matrix such that the difference between this matrix and that matrix is not much. That is, let us say this matrix is X. So you can just convince yourself by that is just by using any kind of mathematical function in say MATLAB or Python. You can just check that its rank is as high as possible. So this is of course a 5x6 matrix, so its rank cannot be more than 5. So you will see that the rank will come to be 5. So it's not a low rank matrix. But the question is it a approximately low rank matrix? That is, can we find a matrix X naught such that the rank of X naught is low, plus if you consider the difference between these two matrices, that is bounded. It's not more than a particular value. So what I have written here is the Frobenius norm of the squared Frobenius norm of this matrix. So like one matrix A minus matrix B is of course another matrix of the same size. Now the Frobenius norm, the squared Frobenius norm of any matrix is basically the sum of the squares of all the elements. So what I am saying is that if you consider another matrix and you take a element by element difference between them and square up all the differences and add them up, it's like something similar to the net error, the squared error between the two matrices. That is not going to be large, it's going to be quite small. So the question, there are results which show, I have already said that if this matrix is low rank, then it is possible for you to to predict the missing values up to a certain level of accuracy. And now I am saying something further. Even if this matrix is itself not low rank, even if it is approximately low rank, then also I can give some guarantee like this. Okay, so now why do I think that this matrix is approximately low rank? I have already said that this is not low rank. That is no, I am not making that claim, but I am still hoping that this is approximately low rank. Now, why do I think that this is an approximately low rank? So because of the spatiotemporal similarity between the different locations. Say if you consider S1 and S2. Okay, so here we can see that S1 and these two rows, S1 and S2, they have roughly the same values. So similarly, if you consider S3 and S4, they have roughly the same value. S5 and S6 roughly have the same values. So it's possible to like if we consider the mean value of both S1 and S2 and just replicate those mean values for along this row as well as on that row, the difference between such a matrix and this matrix will not be very great, right? That is, the Frobenius norm of their difference will actually be small. So seen in that way, we can say that this is an approximately low rank matrix. And since it is an approximately low rank matrix, I can hope to use some of those like those formulations also, using the idea of low rank matrix completion. Okay. So this low rank matrix completion allows us to find the values of the missing value or to estimate all the missing values to a certain to a certain degree of accuracy. Related approach is that of matrix factorization. I'll just end in a couple of minutes. Those who have other classes may leave because the recorded lecture is already available. So the idea here is that suppose the matrix X is a low rank. Okay, and now if the matrix is low rank, let us say its rank is K. Okay, so if it is like we have already considered that is a S comma T matrix. So if it is so if its rank is low, let us say that rank, whatever it is, it's K. Okay, so where K is like much less than both it's much smaller than both S and T. So if that is true, then it's possible to express X as it is possible to decompose X as a product of two matrices A and B, where A is S cross K and B is K cross T. And you can just verify yourself that if, according to the rules of matrix multiplication, that this is fine. That you can do this kind of decomposition. Now the question is how to do this kind of how to find matrices A and B. So there are obviously Sk plus Kt number of variable unknown quantities here. I mean, you do not know any of the elements of A, you do you know any of the elements in B. So and how many elements are in A? Obviously Sk. Similarly in B there are Kt number of unknowns. So you do not know any of these things, but you do know the value of the entries of X. So like if you consider S comma T, it can be written in this way, and just convince yourself that it can, in any element of or any entry of this matrix S can be written out in this way as a like a product and then sum of these unknown values. Now the number now if we have the now in this matrix X, if certain values are missing and but the other values are available, then for each of the available values you can write this kind of an equation. Okay, but how many values are there in this matrix, in this X matrix? There are st number of values, and it is clear because K is much lesser than S and T, it should be obvious that ST has to be much greater than SK plus KT. Okay, now now even if all these values are, all the ST entries are not present, if suppose many of them are are missing, say only a fraction small a, this fraction, let us say small a may be equal to say 0.6 or 0.7 or something like that, or even say it is 0.3, even if that is the case, then also even 0.3 or times st may be much larger than sk plus kt, provided k is small enough. Correct? So that means what? That means for each of the elements of X that are present, you can write it out in front from the form of an equation like this. That is, say like if x11 is visible, I can write it as in terms of a11 b like 11 plus a12 b21 plus a13 plus b31, etc, etc. Similarly, after this, maybe if 1 comma 4 is available, then I can again write it as x11 b14 plus a12 b24 plus etc, etc. You can write it in this way. So you will, for every value which in capital X which you have observed, you can write an equation like this, and clearly these are the number of variables and these are the number of equations. So basically you will get an overdetermined system, that is an overdetermined system of linear equations. Correct? So now if you have an overdetermined system, then using it's possible for you to actually get a least square estimate of all these A's and the B's, right? So and once you have been able to get the values of A and B, since we know that this relation holds, X is equal to AB, then we can easily fill in the values of the or estimate the missing variables also. So that is another thing. This is another approach which you can take. Okay. So yeah, so basically that's all about estimating the missing value. So either you can go for the localized heuristics which we talked about, or you can go for the matrix completion or matrix multiplication based methods. Okay. So if anyone wants to either deliver a seminar later or do the scribe on this topic, that is to say missing value interpolation with the using matrix based methods, they are welcome to do so. Okay. So that brings us to the end of today's class. We are already past time, so we will continue again tomorrow. Thank you.